What if the most Earth-like planet we've ever found isn't actually like Earth at all? Picture a place where the sunsets last for hours, painted in colors no human eye has ever seen. Where rivers of molten lava carve valleys into landscapes under a sky filled with not one, but two blazing suns. This isn't science fiction, it's the reality of exoplanets, worlds beyond our solar system that are rewriting the rules of what makes a planet habitable. Right now, astronomers are uncovering alien environments so strange and spectacular, they challenge everything we thought we knew about where life could exist. From planets with diamond rain to oceans hidden beneath miles of ice, the universe is serving up surprises that even the wildest imaginations couldn't predict. In this video, we're diving into 30 of the most jaw-dropping discoveries in exoplanet science, each one a clue in the greatest detective story of all time. Are we alone in the cosmos? Whether it's a super-Earth with a toxic atmosphere or a distant world where water floats in space like clouds, these findings aren't just cool facts, they're pieces of a puzzle that could determine humanity's future among the stars. So get ready to explore the cutting edge of cosmic discovery, where every new planet is a doorway to the unknown. Imagine a world where the sky doesn't rain water, it rains diamonds. On a distant exoplanet called 55 Cancri, scientists have witnessed exactly that. This super-Earth, twice the size of our own planet and 8 times as massive, orbits so close to its star that its surface is a scorching 2,700 degrees Celsius. Under those blistering conditions, carbon atoms in the atmosphere are crushed together with such intense pressure that they crystallize into diamonds, falling like glittering hail toward the planet's core. This isn't just a poetic metaphor, it's real chemistry unfolding in an alien sky, where the very air transforms into precious gems. What makes this discovery so groundbreaking isn't just the spectacle of diamond showers. It's how it forces us to rethink the basic ingredients of planets. We used to assume most worlds were built from the same rocky or gaseous materials we see in our solar system. But 55 Cancri is carbon-rich, a cosmic oddball where carbon outweighs oxygen, a recipe that would be toxic for life as we know it, yet creates these dazzling geological processes. Even more fascinating, similar diamond-forming conditions might exist right in our own backyard. Deep within Neptune and Uranus, where pressures reach mind-bending levels, scientists suspect trillions of carats of diamonds could be slowly sinking toward their cores. This discovery shatters more than just our expectations. It reveals how little we truly understand about planetary diversity. If carbon-heavy worlds can exist, what other bizarre material combinations are out there? Could there be planets where metals vaporize into clouds, or where oceans of liquid carbon bubble on the surface? Each find like this is a reminder that the universe doesn't play by Earth's rules, and that's what makes exoplanet hunting so thrilling. Who knows what glittering secrets the next distant world might hold? While diamonds rain down on some worlds, others exist in a state of eternal contradiction, half broiled, half frozen, with just a sliver of possibility in between. Take the exoplanet known as K218b, a tidally locked world where one side always faces its star, baking under endless daylight at temperatures hot enough to melt rock, while the other side languishes in permanent night, a frozen wasteland colder than Antarctica. But right along the razor-thin border where these two extremes meet, something remarkable happens, a twilight zone where conditions might just be mild enough for liquid water to exist. This delicate in-between region is like the cosmic equivalent of walking a tightrope too close to the fiery side, and any moisture would evaporate instantly, too far toward the dark and it would freeze solid. Yet here, in this precarious balance, scientists have spotted atmospheric signatures hinting at water vapor. That discovery alone is enough to make astrobiologists lean in closer, because where there's liquid water, there's at least a chance for life as we know it. But how could anything survive in such a mercurial environment? The answer might lie in the planet's atmosphere, which could act like a massive heat-sharing system. Winds might carry warmth from the scorching day side toward the frigid night side, moderating temperatures just enough to keep that twilight band stable. Some researchers even speculate that if microbial life existed there, it could hitch a ride on these atmospheric currents, drifting between zones to survive. It's a far cry from the lush, Earth-like paradises we often imagine, but life has a knack for enduring in the unlikeliest of places. Think of Earth's own extremophiles thriving in boiling hydrothermal vents or buried under glaciers. What's truly revolutionary about this discovery is how it stretches the very definition of a habitable zone. We used to think planets needed to orbit at just the right distance from their star, not too close, not too far. But K2-18b proves that even in the most inhospitable setups, nature might carve out pockets where the impossible becomes plausible. If life can find a way here, in this land of eternal dusk, where does that leave the boundaries of what we consider survivable? The universe, it seems, is far more creative than we ever dreamed. Now picture an ocean, but not one made of water. Imagine waves crashing against alien shores, except these waves are formed from liquid hydrogen shimmering under an alien sun. This is the reality of a newly discovered super-Earth where the very definition of a habitable environment gets turned inside out. Several times larger than our planet, this colossal world exists in a strange twilight zone, too massive to be a traditional rocky planet like Earth, yet not quite a gas giant like Jupiter. Instead, it carves out its own category, with surface pressures so intense they force hydrogen into an exotic liquid state, creating vast, churning seas unlike anything in our solar system. What makes this discovery so revolutionary isn't just the spectacle of a hydrogen ocean, it's the tantalizing possibility of chemistry unfolding in ways we've never witnessed. On Earth, life thrives in water because it's a versatile solvent, capable of dissolving and transporting the molecules essential for biology. But here, in this pressurized alien realm, liquid hydrogen could play a similar role, serving as the stage for reactions we can barely imagine. Scientists speculate that under these extreme conditions, hydrogen might interact with other elements in bizarre ways, potentially giving rise to molecular structures, or even primitive life, that operate on entirely different rules. The real mind-bender, we don't even have the vocabulary yet to describe what that life might look like. Could there be organisms that breathe hydrogen instead of oxygen, or structures that form in the absence of carbon, the backbone of Earth's biology? Some theorists suggest that metallic compounds dissolved in these hydrogen seas might catalyze reactions akin to photosynthesis, while others propose that the planet's crushing gravity could compress hydrogen into strange, superconductive forms capable of conducting energy in ways that defy known physics. This isn't just about adding another oddity to the cosmic menagerie. It's about rewriting the playbook for where and how life might arise. If a planet like this can exist, then the boundaries of habitability stretch far beyond the Goldilocks zone we once considered the only arena for life. Suddenly, the icy moons of gas giants or even rogue planets drifting between stars seem like potential incubators for chemistry we've yet to dream of. And that's the thrill of exoplanet science. Every discovery doesn't just answer questions, it reinvents them. Who's to say what other liquid landscapes might be waiting out there, defying our expectations in ways we can't yet fathom? Some planets don't just endure the heat of their stars, they wear it like a shimmering cloak of vaporized metal. Imagine a world where the air isn't filled with nitrogen or oxygen, but with swirling clouds of iron and titanium glowing like embers in a cosmic furnace. This is the reality of ultra-hot exoplanets like Kelt 9b, a gas giant so close to its star that its daytime temperatures exceed 4,000 degrees Celsius hotter than some stars. At those extremes, metals on the surface don't just melt, they boil straight into the atmosphere, creating a bizarre metallic haze that rains back down as the planet's night side cools. These aren't just exotic curiosities, they're cosmic laboratories revealing how planets evolve under extreme stress. Normally, atmospheres are shaped by gentle processes like weathering or volcanic outgassing. But on these blistering worlds, the very rock itself is being stripped away, atom by atom, as stellar winds blast metal vapors into space. Scientists call this atmospheric escape, and it's happening at a staggering scale. Some of these planets are losing the equivalent of an Earth's worth of mass every billion years. Yet despite the violence, there's a strange beauty in how these metals glow when caught by telescopes. Spectroscopic analysis splits their light into rainbows, revealing fingerprints of iron, titanium, even chromium, all dancing in superheated winds. What's most surprising is how these discoveries are rewriting the rules of planetary survival. We used to think gas giants like Jupiter were relatively stable, but these metal-rich worlds show how volatile giant planets can be when pushed to their limits. Some might eventually erode entirely, leaving behind nothing but a scorched core planetary ghost. Others could forge entirely new kinds of atmospheres as lighter elements boil off, leaving heavier metals behind like a celestial distillation process. But here's the real kicker. This isn't just happening in far-off star systems. Billions of years ago, when our own solar system was young, Mercury might have endured a similar fate, its surface scorched away by a younger, fiercer sun. That means studying these distant metal worlds isn't just about cataloging oddities. It's about piecing together the violent history of planets everywhere, including our own cosmic neighborhood. Every metallic breath these planets exhale tells a story, one where fire and metal shape worlds in ways we're only beginning to understand. Deep in the void between stars where no sunlight ever reaches, a lone planet drifts untethered, invisible, and yet somehow alive with light. This isn't a frozen wasteland as you might expect, but a rogue world pulsing with shimmering auroras, painting the darkness in hues of violet and green. Unlike Earth's northern lights, fueled by solar winds crashing into our atmosphere, these alien light shows have a far more mysterious origin. With no host star to bombard it with charged particles, this nomadic planet generates its own magnetic fireworks through the sheer heat of its churning core, turning the emptiness of space into an unexpected cosmic canvas. What's truly startling about these wandering worlds isn't just their eerie beauty, it's the possibility that they could harbor secrets beneath their surfaces. Without a sun to warm them, scientists once assumed rogue planets were little more than frozen relics, doomed to drift in perpetual ice. But the energy powering those auroras suggests something far more intriguing. Residual geothermal heat, left over from their violent births, might still be bubbling beneath the surface. And where there's heat, there's potential for liquid water, or even vast subsurface oceans insulated from the freezing vacuum by miles of ice or rock. Suddenly, the definition of habitable takes another wild twist. If life can thrive near hydrothermal vents at the bottom of Earth's oceans, cut off from sunlight and surviving on chemical energy alone, why not in the hidden seas of a rogue planet? Some researchers speculate these nomadic worlds could be far more common than we thought, outnumbering stars in our galaxy by the billions, each one a dark horse candidate in the search for life. They might even serve as cosmic lifeboats carrying microbial hitchhikers between star systems, seeding the galaxy in a slow-motion diaspora. But the most tantalizing question remains: what would life look like in such an isolated environment? No day or night cycle, no seasons, just endless darkness punctuated by the glow of auroras from below. evolution would have to craft survival strategies never seen on Earth, perhaps organisms that harvest energy from magnetic fields or chemical gradients in the abyss. It's a reminder that the universe doesn't need a star to write a recipe for life, just a little heat, a dash of chemistry, and a whole lot of cosmic creativity. Who knows how many of these invisible wanderers might be hiding oceans, or even civilizations under their icy shells, passing unseen through the night. Most planets know a simple rhythm: one sunrise, one sunset, a predictable dance of light and dark. But in a distant star system over 300 light-years away, a planet experiences something far more surreal. Triple sunrises painting the sky in shifting hues, followed by not one but 3 sunsets each day. This is HD 131399 AB, a world locked in an intricate gravitational ballet with not just one star but 3. 2 of these stars pirouette around each other like cosmic dancers, while the third loops around them both, casting ever-changing shadows across the planet's surface. The result, a light show that puts Earth's finest sunsets to shame. Fiery oranges bleeding into deep violets as the stars align and separate in an endless celestial waltz. Yet this spectacle comes at a cost. With 3 stars tugging at its orbit, the planet's path through space is anything but stable. Some years it swings close to one star, basking in scorching heat. Other times it's flung toward the outskirts of the system where temperatures plummet. These wild swings create seasons unlike anything we've seen. Not the gentle progression of spring to summer, but abrupt, violent shifts between extremes. One moment, the surface might be baked into a cracked desert, the next frozen beneath glaciers that form almost overnight. For life as we know it, this seems like a death sentence. How could anything survive such chaos? But here's where nature throws us a curveball. Some astrobiologists argue that these very fluctuations could create opportunities for life, not just destroy them. Think of Earth's most resilient organisms, bacteria that hibernate in Antarctic ice, or microbes thriving in boiling acid springs. On a planet with triple suns, life might evolve to go dormant during brutal heat waves or ice ages, only to burst into activity during rare moments of balance. There's even a chance that tidal forces from the star's gravity could keep underground oceans liquid, hidden beneath the surface where temperatures stay stable. This discovery doesn't just add another oddity to the exoplanet zoo. It forces us to rethink one of astronomy's oldest assumptions, that life needs the steady rhythm of a single sun to flourish. If a world like this can carve out niches of habitability amid stellar chaos, then maybe life isn't as fragile as we thought. Perhaps it's more like cosmic moss, finding cracks in the universe's harshest environments and clinging on against all odds. And if that's true, how many other improbable oases might be waiting in the turbulence of multiple star systems? The answer could rewrite not just where we look for life, but what we believe life is capable of enduring. Imagine a planet where the only land is an illusion, where every mountain has drowned beneath a crushing, endless ocean, stretching from pole to pole without a single shoreline to break the waves. This is the reality of a newly discovered water world, an exoplanet so saturated that its entire surface is swallowed by a global sea hundreds of kilometers deep. At first glance, it might seem like a paradise for life, with liquid water as far as the eye could see. But dive deeper, literally, and the rules of physics twist into something alien. Near the surface, the ocean behaves like water on Earth, but descend far enough, and the pressure becomes so immense that the water molecules themselves rearrange, freezing into exotic forms of ice, not the fluffy snowflakes we know, but dense, hot ice that defies intuition by forming at temperatures that would boil water on our planet. This isn't just a curiosity, it's a laboratory for extremes. On Earth, life clusters around hydrothermal vents, where mineral-rich water fuels ecosystems in total darkness. Here, in this abyssal world, similar vents might spew nutrients into the eternal deep. But could anything survive under pressures that would crush submarines like tin cans? Some scientists speculate that life here would need to evolve without surfaces altogether, drifting in vast, slow currents or anchoring itself to icy layers like cosmic kelp. Others argue the chemistry might be too stifling, with no land to cycle minerals or regulate acidity. Yet the most profound implication isn't just about life, it's about how planets age. Earth's oceans are shallow compared to this world's. Over billions of years, our water has been sequestered in minerals or lost to space. But this planet's overwhelming reserves could mean it's locked in a perpetual state of youth, its water too deep to escape or be absorbed. That raises a haunting question. Is our own blue planet the exception, or are we just a temporary phase in a water world's lifespan, destined to dry out while others drown? What's clear is that this discovery blurs the line between ocean and planet. We're not looking at a world with water, we're looking at water that's become a world. And if life can find a way here in the crushing dark, then maybe the universe's favorite recipe for life isn't land and sea, but patience and pressure, two ingredients this planet has in infinite supply. At the edge of what a planet can endure, where temperatures turn rock to vapor, scientists have spotted a world wrapped in a shimmering metallic veil. This exoplanet doesn't just have an atmosphere, it wears a cloak of titanium oxide, a compound so reflective it turns the sky into a colossal mirror. On Earth, titanium oxide is the stuff of sunscreen and white paint, scattering light to protect or brighten. But here, under the blistering glare of its host star, this compound forms a permanent haze so dense it bounces a staggering amount of heat back into space, creating a paradox, a planet that's searingly hot yet cooler than it should be. This discovery cracks open a mystery that's puzzled astronomers for years. Ultra-hot Jupiters, gas giants orbiting dangerously close to their stars, should be some of the most infernal places in the cosmos. Yet some defy expectations, their temperatures oddly muted. Now we know why their skies aren't just filled with gas, they're laced with microscopic metallic particles that act like a planetary sunshade. Imagine standing on the surface of such a world. The air itself would glitter, scattering light in every direction, while the ground below might simmer in a dimmer, diffused glow, as if the entire planet were draped in a celestial silk sheet. But the implications go far beyond atmospheric curiosities. This titanium haze is like a cosmic thermostat, regulating how much stellar energy the planet absorbs. That means our models for predicting exoplanet climates just got a major upgrade. If reflective compounds like this are common, we might need to rethink how we define a hot Jupiter, and even how we search for habitable worlds. After all, if a planet can naturally engineer its own cooling system, perhaps others use different compounds to fine-tune their temperatures in ways we've yet to imagine. What's truly game-changing is how this discovery could shape the next generation of telescopes. If we want to study exoplanet weather, weather on worlds light years away, we'll need instruments capable of detecting these elusive metallic hazes. Future observatories might be tuned to spot the unique fingerprints of titanium oxide or similar compounds, peeling back the layers of alien skies to reveal how they sculpt their own climates. It's a reminder that the universe doesn't just build planets, it accessorizes them, wrapping them in atmospheres that can dazzle, deceive, and rewrite the rules right before our eyes. Some planets don't just have volcanoes, they live and breathe through them, their surfaces pulsing with eruptions that never cease. That's the reality of this fiery super-Earth, a world where the ground itself is in constant rebellion, splitting open in countless fiery wounds that bleed rivers of molten rock across the landscape. Unlike Earth's occasional volcanic outbursts, this planet endures eruptions on a scale that would make Mount Vesuvius look like a campfire, all thanks to an unforgiving gravitational tug of war with its nearby star. What makes this discovery so extraordinary isn't just the spectacle of perpetual lava flows, it's the window it gives us into Earth's own violent infancy. Billions of years ago, before our continents settled into place, our planet may have looked much like this, a roiling cauldron of magma oceans and relentless eruptions, its crust endlessly recycled in the furnace below. Studying this distant world is like finding a cosmic time capsule, letting us witness the processes that likely shaped our own atmosphere and oceans. Those ancient earthly volcanoes belched out the gases that formed our air and the water vapor that filled our seas. Could the same be happening right now on this distant super-Earth? But there's a twist. This planet's volcanism isn't powered by internal heat alone. It's locked in an orbital dance so extreme that its host star's gravity stretches and compresses the planet like putty, generating friction that keeps its interior perpetually molten. The result is a world caught between fire and gravity, one side permanently scorched by stellar radiation, the other churned by tides so strong they could reshape mountains in a single orbit. The burning question isn't just about geology, it's about life. On Earth, volcanic vents in the deep ocean became cradles for early life, their mineral-rich plumes feeding the first microorganisms. Could similar oases exist in this planet's lava-riddled crust? The odds seem slim, with surface temperatures capable of vaporizing rock, but beneath the chaos, in subterranean chambers insulated from the inferno above, who knows what chemistry might be brewing? Perhaps most intriguing is what this world teaches us about planetary evolution. Volcanism isn't just destruction, it's renewal. The same forces that ripped this planet apart may also be recycling its surface, releasing gases that could one day cool its climate or providing the raw materials for future oceans. It's a reminder that today's hellscape might be tomorrow's haven, and that somewhere out there, another young planet could be following the same fiery path Earth once took toward becoming a living world. Some planets don't just orbit their stars, they disintegrate before our eyes, leaving behind a celestial wake like a cosmic breadcrumb trail. Take P32b, a gas giant so close to its sun that it's literally boiling away, its atmosphere ripped into a million-degree tail of ionized gas stretching over 500,000 kilometers into space. From a distance, this planet looks less like a world and more like a comet, its shimmering plume a beacon of destruction and revelation. What's startling isn't just the spectacle of a planet unraveling in real time, but what it tells us about the hidden battles every planetary system faces. Atmospheric escape isn't new. Earth loses about 90 tons of air to space every day, but here, the violence is dialed to extremes. The planet's host star bombards it with ultraviolet radiation, heating its hydrogen atmosphere until it balloons like a runaway hot air balloon, then gets shredded by stellar winds. Telescopes have caught this drama mid-act, watching as the planet's outer layers are vacuumed into the void, leaving a ghostly trail visible across light years. Yet this tragedy holds clues to cosmic survival. Scientists believe similar processes might have shaped Mars, a world once wrapped in a thick atmosphere, now barren after its gases were stripped away over eons. By studying P32b, we're witnessing a time-lapse of planetary evolution. What took Mars billions of years to lose, this gas giant sheds in centuries. That speed lets us test theories about how planets die, or in rare cases, how they might adapt. Some worlds could cling to life by migrating outward, escaping their star's wrath like a ship fleeing a storm. Others might transform entirely, their molten cores laid bare as their gaseous envelopes vanish, leaving behind rocky skeletons we'd barely recognize as planets. The real stunner, this isn't just about the past, it's about the future. Our own Jupiter might have started as a hot Jupiter like this one, its atmosphere seared before it retreated to the safety of the outer solar system. And if that's true, then these evaporating worlds aren't just casualties. They're time capsules showing us the fiery trials that shape planetary systems everywhere. Every atom lost to that glittering tail is a piece of the puzzle, one that could rewrite the story of how planets and maybe even life find a way to endure. The fiercest storm you've ever seen would barely qualify as a breeze on this exoplanet, a world where cyclones don't just form, they dominate, stretching wider than the planet itself and raging with winds that could shred continents. Picture Jupiter's great red spot, but magnified to monstrous proportions, a swirling vortex so vast it could swallow stars whole. This isn't atmospheric drama, it's atmospheric supremacy, where weather doesn't just happen, it rains. What fuels these mega storms? It's a perfect recipe of cosmic extremes. The planet's breakneck rotation, spinning so fast a single day lasts mere hours, whips its atmosphere into a frenzy. Meanwhile, the temperature contrast between its scorching day side and frozen night side acts like a colossal engine, driving winds that exceed 8,000 kilometers per hour. These aren't just gusts, they're hypersonic rivers of gas carving through the atmosphere like invisible tidal waves. But here's the real puzzle. These cyclones don't behave like storms on Earth or even Jupiter. Instead of dissipating, they merge, growing larger and more violent over time, like celestial tempests feeding on their own fury. Scientists suspect the planet's lack of solid ground plays a role. With no mountains or oceans to disrupt airflow, the storms spiral unchecked, evolving into structures so stable they could outlive civilizations. Studying these cyclones isn't just about cataloging cosmic weather anomalies. It's a window into how energy flows through alien atmospheres, rewriting the rules of fluid dynamics on planetary scales. Climate models designed for Earth buckle under these conditions, forcing researchers to invent entirely new equations to predict how such storms form and what they might mean for habitability. If a planet's atmosphere is locked in perpetual chaos, could life find refuge in calm pockets beneath the turbulence, or would it be snuffed out by endless violence? Perhaps the most humbling lesson is how small our terrestrial perspective really is. We think of hurricanes as disasters, but on this world, they're the baseline, a reminder that the universe doesn't just host milder versions of Earth's weather. It invents its own rules, crafting storms so magnificent they redefine what a sky can do. And if that's true, what other atmospheric wonders might be waiting in the dark, spinning silently around stars we've yet to discover? Beneath an alien sky where the ground itself glitters with unearthly riches, lies a planet that turns geology into alchemy. This carbon-cloaked world isn't built on rock as we know it. Instead, its entire surface is a patchwork of graphite plains and diamond-veined mountains, forged in a stellar environment where carbon outnumbers oxygen 10 to 1. Unlike Earth's silica-dominated crust, born from a cosmic abundance of oxygen, this planet is a relic of a different recipe, one where soot might be soil and gemstones are as common as gravel. The implications ripple far beyond the spectacle. For decades, astronomers assumed most rocky planets would resemble Earth's basic chemistry. After all, silicon and oxygen dominate our solar system. But this discovery shatters that assumption, proving the universe has more than one way to bake a planet. Imagine continents not of granite but of layered graphene, valleys carved by rivers of tar like hydrocarbons, or even towering diamond formations sculpted by millennia of carbon rain. Under the right conditions, these exotic materials could create landscapes both alien and familiar, mountains that refract sunlight into rainbows, or plains as slick and conductive as industrial electrodes. What's truly revolutionary is how this rewrites the search for life. Earth's carbon-based biology depends on a delicate balance. Too little carbon, and life's building blocks vanish. Too much, and the planet chokes under a smoggy haze. But here, where carbon drowns every other element, could life adapt to use graphite as its scaffolding? Some astrobiologists speculate about organisms with cellular walls reinforced by diamondoid structures, or metabolic processes that tap into the planet's vast carbon reservoirs for energy. Others argue the excess carbon would create a suffocating atmosphere, thick with organic smog, a greenhouse nightmare where only the hardiest extremophiles might cling to existence. The bigger picture, planets like this might be cosmic chameleons. While our solar system favors oxygen-rich environments, others could be carbon kingdoms, their chemistry dictated by the unique composition of their birth clouds. If that's true, then the Milky Way could harbor entire lineages of worlds we've never dreamed of, planets where carbon isn't the guest of honor, but the architect of everything. Each one a reminder that the universe doesn't just recycle the same blueprint, it improvises, experiments, and occasionally crafts a world where the very ground beneath your feet defies imagination. While Earth's water cycle is the heartbeat of our planet's climate, imagine a world where rivers don't flow with water, they flow with liquid methane, carving valleys into frozen ground under a dim, reddish sun. This is the reality of an exoplanet where the hydrologic cycle runs on an entirely different chemistry, one that transforms methane into clouds, rain, and even lakes, mirroring Earth's water cycle, but at temperatures cold enough to freeze nitrogen solid. On this distant world, the methane cycle isn't just a curiosity, it's the lifeblood of its weather. As the feeble starlight warms the surface, methane evaporates from vast hydrocarbon lakes, rising into hazy orange skies before condensing into thick, smog-like clouds. When conditions are right, these clouds unleash downpours of methane rain, filling riverbeds and pooling in basins just like water does here, but that's where the similarities end. Because methane's properties are so different, less sticky than water, quicker to evaporate, the planet's landscapes could be shaped by flash floods and sudden droughts, with shorelines that shift dramatically over seasons. What makes this discovery groundbreaking isn't just the spectacle of alien meteorology. It's how it forces us to rethink the very ingredients needed for a dynamic, evolving world. Earth's water cycle is vital for life as we know it, distributing nutrients and moderating temperatures. But if methane can play the same role at cryogenic temperatures, suddenly, the coldest corners of the galaxy seem a lot more interesting. Moons like Titan in our own solar system already hint at this possibility, with their methane rivers and ethane lakes, but finding a full-fledged methane cycle on an exoplanet suggests this isn't a fluke. It might be a common alternative to water in frigid star systems. The real tantalizing question, could life hitch a ride on this methane merry-go-round? On Earth, extremophiles thrive in places once thought uninhabitable, from acidic hot springs to Antarctic ice. If microorganisms here can metabolize methane in oxygen-free environments, why not on a world where methane is the dominant liquid? Some astrobiologists speculate that methane-based life wouldn't need water at all. It might use liquid hydrocarbons as its solvent, crafting biochemistry from molecules we've barely considered. This discovery doesn't just add another planet to the catalog, it cracks open the door to an entirely new class of habitable worlds. If a methane cycle can sustain geology and climate, then the universe's recipe for Earth-like just got a lot more flexible. And that means the search for life isn't limited to planets with balmy oceans and blue skies. Some of the most promising real estate in the cosmos might be the frigid, orange-hazed worlds where the rivers run with something far stranger than water. Some atmospheres don't just scatter light, they create their own. Picture a world where the sky doesn't just shine with reflected starlight, but pulses with a soft, otherworldly luminescence, like a cosmic neon sign flickering in the void. This isn't science fiction, it's the reality of a distant exoplanet whose upper atmosphere emits its own eerie glow. A phenomenon so rare it's rewriting how we search for life beyond Earth. What causes this radiant spectacle? The answer lies in a delicate dance between chemistry and radiation. As ultraviolet light from the planet's star bombards its atmosphere, it tears apart molecules of hydrogen and nitrogen, sending their atoms spiraling into chaotic collisions. When these shattered pieces reassemble, they release energy in the form of light, a process similar to what makes auroras glow, but spread across the entire sky instead of just the poles. The result is an ethereal haze, faint enough to miss at first glance, but unmistakable once telescopes tune to the right wavelengths. But here's where things get truly tantalizing. While this glow could simply be the product of exotic chemistry, there's a chance, however slim, that it might hint at something more profound: life. On Earth, certain microorganisms produce similar faint emissions through chemical reactions, and some scientists speculate that alien lifeforms might do the same on a planetary scale. Imagine entire ecosystems of organisms whose metabolisms release phosphorescent byproducts, turning their atmosphere into a beacon visible across light years. It's a long shot, but the mere possibility has researchers scrambling to distinguish between biological and non-biological explanations. The key lies in the glow's fingerprint. If the light contains specific patterns or unexpected chemical signatures like oxygen mixed with methane in unstable combinations, it could point to biological activity. But if it's just the product of raw stellar fury interacting with common gases, then we're witnessing a stunning natural phenomenon, not a sign of life. Future telescopes designed to analyze atmospheric chemistry in extreme detail might finally settle the debate, peeling back the layers of this radiant enigma. What's undeniable is how this discovery stretches the boundaries of what we consider a living planet. We've long searched for Earth-like worlds with familiar features: blue skies, liquid water, temperate climates. But if life can paint an entire sky with its own glow, then maybe the most promising biosignatures aren't the ones we expect, but the ones we've yet to imagine. And that means the universe's recipe for life might be written in light we're only just learning to see. Most planets wear their magnetic fields like a steady cloak, but not this one. Imagine a world where the very forces shielding it from space's fury are in constant rebellion, flipping north and south in chaotic bursts like a compass gone mad. This isn't just a planetary oddity, it's a cosmic gamble where the magnetic field doesn't just weaken or shift gradually, but reverses polarity entirely at random intervals, leaving the surface vulnerable to deadly cosmic rays for months or even years at a time. What makes this phenomenon so startling is how it defies everything we know about planetary magnetism. Earth's own magnetic field flips too, but over millennia, giving life plenty of time to adapt. On this exoplanet, the reversals happen in a celestial heartbeat with no warning or pattern. One moment, the field might deflect solar storms with ease. The next, it collapses entirely, leaving the atmosphere exposed like an open wound. Radiation that would normally bounce harmlessly away instead pours onto the surface, sterilizing landscapes and shredding any fragile chemistry that might hint at life. Yet here's the twist: this instability might not be a death sentence. Some researchers speculate that these violent flips could actually stir a planet's interior, churning its molten core to generate even stronger magnetic bursts after each reversal. It's like a cosmic reset button, disruptive in the short term, but potentially rejuvenating over geologic time. There's even a chance that life, if it existed here, could retreat underground during these chaotic periods, sheltering in caves or deep oceans until the magnetic shield reforms. But the real question isn't just about this one world. It's about how many others might be hiding similar volatility. If magnetic instability is common, especially among smaller, rocky planets, then our search for habitable worlds just got a lot more complicated. We used to assume a stable magnetic field was non-negotiable for life. Now, we might need to consider that habitability isn't an on-off switch, but a pendulum swinging between danger and opportunity with every flip of the cosmic currents. What's certain is that this discovery forces us to rethink the rules of planetary protection. A magnetic field isn't just a static force, it's a living, breathing entity, capable of wild mood swings that shape the fate of entire worlds. And if that's true, then the universe might be full of planets playing a high-stakes game of magnetic roulette, each one a roll of the dice between sanctuary and storm. Think Saturn's rings are impressive. They're just a modest accessory compared to the cosmic spectacle around this newly discovered exoplanet, a gas giant wrapped in rings so vast they could swallow our entire solar system's ringed planets whole. Stretching millions of kilometers into space, this colossal ring system doesn't just dwarf Saturn's. It periodically blots out its own star, casting shadows so deep they're visible across interstellar distances. Imagine standing on a moon within those rings. The sky wouldn't just be streaked with delicate bands of ice and dust. It would be dominated by a towering wall of debris, curving endlessly into the darkness like a celestial fortress. What's truly baffling isn't just the scale of these rings, it's how they even exist at all. Normally, rings this massive should collapse under their own gravity, coalescing into moons or scattering into space. Yet here they are, defying expectations. Scientists suspect the planet's unusual orbit might hold the key. Unlike Saturn, which sits comfortably in the calm of our solar system, this world might be locked in a gravitational tug of war with neighboring giants, their tidal forces stirring the rings like a cosmic spoon, preventing them from clumping together. Or perhaps the rings are the shattered remains of a moon torn apart by the planet's gravity. A moon so large its fragments are still spiraling in a slow-motion avalanche. But here's the electrifying possibility. Hidden within those rings could be moonlets, tiny worlds cloaked in debris, shielded from radiation and warmed by tidal forces. If even one of these moonlets orbits at just the right distance, it might trap enough heat to sustain subsurface oceans, much like Saturn's Enceladus or Jupiter's Europa. The difference, these potential ocean worlds wouldn't orbit a calm, solitary planet. They'd whirl through a labyrinth of ice and rock, where the skies are forever split by the glare of sunlight bouncing off countless ring particles. The implications are staggering. If life could thrive in the hidden oceans of our solar system's icy moons, why not here? These moonlets might be the ultimate cosmic hideouts, protected by their rings from asteroid impacts, their interiors churned by gravitational tides, their chemistry enriched by the constant rain of organic rich ring material. It's a reminder that habitability doesn't always mean Earth-like. Sometimes it's tucked away in the unlikeliest of places, like a speck of warmth in a storm of frozen debris, spinning silently in the shadow of a ringed giant. And that's the real magic of this discovery. It's not just about the rings themselves, it's about the secrets they might conceal. Every time we find a planet that breaks the mold, it's like the universe is whispering, "You haven't seen anything yet." So while Saturn's rings will always captivate us, this distant giant's mammoth halos are proof that the cosmos still holds wonders beyond our wildest dreams, and perhaps life in forms we've yet to imagine. Most planets settle for one atmosphere. This one wears two, like a cosmic layered costume. Picture a world where the sky isn't a seamless blend of gases but a stark divide, as if an invisible line splits the air into two alien realms. Above, a lightweight veil of hydrogen ripples like a translucent curtain, barely clinging to the planet. Below, a dense shroud of heavier gases, carbon dioxide, nitrogen, maybe even traces of sulfur presses down with the weight of a perpetual thunderhead. This isn't just atmospheric variation, it's a planetary identity crisis where two completely different skies share the same world. What makes this discovery so baffling isn't just the layering, it's how the two atmospheres refuse to mix. On Earth, our winds and storms churn the air into a relatively uniform blend, but here, some unseen force keeps these layers locked in their own domains, like oil floating on water. Scientists suspect the planet's extreme gravity might be the culprit, acting like a cosmic bouncer that sorts gases by weight. Lighter hydrogen bobs to the top, while heavier elements sink, creating a stratification so sharp it defies conventional climate models. But here's where it gets even weirder. These layers might be interacting in ways we've never seen. The upper hydrogen envelope could be slowly evaporating into space, stripped away by stellar winds, while the lower atmosphere remains stubbornly anchored. That means this planet could be caught in a slow-motion transformation, shedding one identity while clinging to another. It's like watching a celestial molting process where the outer skin peels away to reveal something entirely different underneath. The implications for habitability are dizzying. Normally, we look for atmospheres with the right mix of gases to sustain life. But what if a planet could hide its true atmosphere beneath a decoy layer? Imagine a world where the upper hydrogen veil masks a breathable nitrogen-oxygen blanket below, or worse, where a seemingly hospitable outer layer conceals a toxic underbelly. This discovery forces us to question whether we've been reading alien skies all wrong, mistaking costumes for climates. Perhaps the most revolutionary takeaway is how this double-decker atmosphere challenges our very definition of planetary boundaries. We used to think of atmospheres as single, cohesive systems. Now, they might be more like layered cakes, each tier with its own recipe, its own weather, even its own rules. And if that's true, then the universe just handed us a new set of mysteries to unravel, one atmospheric layer at a time. Locked in a never-ending scream of wind, this exoplanet wages war with itself. One side perpetually scorched by its star's fury, the other lost in frozen darkness, and between them a hurricane that refuses to die. Unlike Earth's storms that rage for days or weeks before dissolving, this tempest has churned for centuries, maybe millennia, a fixed maelstrom spinning like a top on the planet's sunlit face. The violence is beyond anything in our solar system. Winds that could outpace jetliners, clouds of vaporized rock, and rains that might carry not just water, but the building blocks of life itself. What keeps this hurricane alive isn't just heat. It's the stark divide between day and night on a tidally locked world. The star-facing side bakes at temperatures hot enough to melt lead, while the dark side plunges to hundreds of degrees below zero. That extreme contrast acts like a colossal engine, driving air currents in a relentless loop. Hot gases explode upward from the day side, only to crash back down as they cool over the night side, creating a self-sustaining vortex that feeds on its own chaos. It's a storm without end, trapped in a planetary-scale convection oven. But here's the twist that has scientists buzzing. Within those swirling clouds, telescopes have detected organic molecules, carbon-based compounds that on Earth are the precursors to life. Normally, such fragile chemistry would be torn apart by hurricane-force winds. Yet on this world, the very violence of the storm might be protecting and mixing these ingredients, stirring them like a cosmic blender. Some researchers compare it to Earth's early oceans, where turbulence and lightning sparked complex chemistry. Could the same be happening in this alien maelstrom? The implications are as wild as the weather. If life needs energy, this hurricane provides it in spades: kinetic energy from the winds, thermal energy from the temperature swings, even electrical energy from the friction of colliding particles. And if life needs nutrients, the storm's endless churn could be dredging them up from deep underground, lofting them into the atmosphere like a perpetual geyser. It's a radical idea that a place too hostile for calm might be just chaotic enough to cook up something unexpected. Of course, the odds are slim, but they're not zero. Earth's own extremophiles thrive in scalding vents and acid pools, proving life can cling to existence in the unlikeliest corners. Maybe on this world, the hurricane isn't the end of the story. Maybe it's the beginning, a reminder that sometimes the universe doesn't build life in quiet ponds, but in the eye of the storm. Beneath a frozen crust so thick it could bury mountains, an entire ocean churns in perpetual darkness, not on some distant moon, but on a rogue exoplanet drifting between the stars. This isn't just any water, it's a subsurface sea warmed by the planet's own fiery heart. Its heat bubbling up through hydrothermal vents like underwater volcanoes, creating oases of warmth in an otherwise icy tomb. Scientists spotted clues to this hidden ocean not by seeing liquid directly, but by detecting odd gravitational tugs and magnetic fluctuations, hints that something massive and electrically conductive like salt water was sloshing beneath the ice. What makes this world so extraordinary isn't just the water, it's the fortress protecting it. Above the ocean stretches an ice shell dozens of kilometers thick, a natural radiation shield so effective it could outpace anything humans could engineer. While the surface languishes in bitter cold, untouched by sunlight for billions of years, the depths below might be as cozy as Earth's deep sea trenches, where geothermal heat fuels entire ecosystems. It's a paradox, a planet that looks like a frozen wasteland from space, but could harbor more liquid water than all of Earth's oceans combined. The echoes of our own solar system are uncanny. Europa and Enceladus, icy moons around Jupiter and Saturn, are thought to hide similar subsurface seas, but finding an exoplanet with the same recipe suggests these aren't cosmic flukes. They might be galactic norms, hidden aquatic worlds waiting in the dark. And if that's true, the implications for life are staggering. On Earth, hydrothermal vents teem with creatures that thrive without sunlight, powered by chemical energy alone. Could similar life exist in these lightless alien oceans, clustered around vents spewing minerals into the abyss? The real game changer is how these planets could outlast traditional habitability. While surface oceans evaporate or freeze over billions of years, subsurface ones insulated by ice might persist for trillions, offering life a refuge long after stars fade. Imagine civilizations arising not under open skies, but in labyrinthine ice caves, their world lit by bioluminescent lifeforms and geothermal glow. Or simpler, microbes drifting in endless blackness, unaware of the universe above. This discovery does more than add another candidate to the search for life. It flips the script on where we should be looking. The most promising real estate in the cosmos might not be Earth-like planets with sunny shores, but frozen outliers. Their warmth locked inside, their oceans hidden like secrets, waiting for someone or something to dive beneath the ice. Some planets wear their scars like badges of honor. This one flaunts its wounds to the cosmos. A survivor of a cataclysm so violent it left its metallic heart exposed for all to see. Scientists have spotted an exoplanet with a surface torn open, revealing the glowing innards of what was once a hidden core, like a cosmic fruit peeled by some unimaginable force. The damage isn't just superficial. This world's very skeleton is laid bare, its iron-rich core pulsing with residual heat and magnetism under a sky littered with the debris of whatever collision nearly tore it apart. What makes this discovery so extraordinary isn't just the brutality on display, it's the chance to study planetary anatomy in a way we've never been able to before. On Earth, we can only guess at what lies beneath our feet, relying on seismic waves and lava samples to piece together our planet's inner workings. But here, the crust has been ripped away like a curtain, exposing the machinery of planetary formation in real time. The exposed core crackles with magnetic activity, generating auroras that flicker in the thin remnants of an atmosphere, while volcanic vents spew molten metal, not rock, into rivers that cool into bizarre metallic landscapes. The implications ripple far beyond geology. Planetary collisions aren't rare. Our own moon was likely born from a similar cataclysmic impact early in Earth's history. But witnessing the aftermath of such violence gives us a front-row seat to the forces that shape rocky worlds. This planet's magnetic field, for instance, is both weaker and more erratic than expected, suggesting that even a core as massive as this one can be destabilized by trauma. That's a crucial clue for understanding how planets like Mars lost their protective magnetic shields, dooming their atmospheres to erosion over time. But here's the twist: this world isn't dead. Despite the apocalyptic damage, residual volcanic activity hints at a stubborn geothermal heartbeat. Some researchers speculate that the exposed core might actually be rejuvenating the planet, its heat driving new geologic cycles that could, over eons, rebuild a shattered surface. It's a reminder that destruction and creation are two sides of the same cosmic coin. What looks like an ending might just be a violent new beginning, the real revelation. Planets like this might be more common than we thought. If collisions of this scale aren't just ancient history but ongoing events, then the universe is far more chaotic and creative than our tidy models suggest. And if that's true, then every rocky world we've ever studied, including Earth, might carry similar scars beneath its skin, hidden reminders of the brutality that forged it. This planet isn't just a cautionary tale, it's a mirror showing us how fragile and how resilient worlds like ours really are. If planets had personalities, this one would be the ultimate cosmic rebel, a world that defies the most basic rule of orbital motion by spinning backward around its star. While most planets in a system move in sync with their star's rotation, like dancers in a celestial waltz, this rogue exoplanet breaks formation entirely, tracing its path in the exact opposite direction. It's as if Earth suddenly decided to orbit the Sun clockwise while the rest of the solar system carried on counter-clockwise, a cosmic act of defiance that shouldn't even be possible under normal circumstances. What makes this backward orbit so baffling isn't just the oddity of its motion, it's the violence required to flip a planet's trajectory in the first place. Scientists suspect this world didn't start out as a rebel. Instead, it was likely yanked off course by a gravitational showdown, perhaps a close encounter with another massive planet, or even a passing star that sent it spiraling into this topsy-turvy path. Imagine a game of planetary pinball, where one collision or near miss was enough to send this world careening in the wrong direction, forever out of step with its stellar family. The discovery is more than just a celestial curiosity, it's a wrench thrown into the gears of planetary migration theories. For decades, astronomers assumed planets formed in orderly, co-rotating disks of gas and dust, settling into stable orbits over time. But this backward world proves that chaos can rewrite the rules long after a planet's birth. Some systems might be far more dynamic and far more volatile than we ever imagined, with gravitational tussles that can fling worlds into bizarre configurations. Here's where it gets even wilder. This retrograde orbit might not be a death sentence. Despite its turbulent past, the planet could have stabilized over time, carving out a new equilibrium in its backward dance. That adaptability hints at a universe where even the most disruptive events don't necessarily doom a planet, they just force it to find a new normal. But the real revelation: this backward world might not be alone. If one planet can flip its orbit, others might have similar stories hidden in plain sight, waiting for us to notice. THEIR Chinese letter journeys. And if that's true, then every orderly star system we've ever studied might have a rebellious sibling lurking in its past, a reminder that the cosmos loves to throw curveballs when we least expect them. Among all the strange and wondrous exoplanet discoveries, few have sent shockwaves through the scientific community like the detection of phosphine gas in a distant world's atmosphere. This toxic, flammable compound might not sound impressive at first, until you learn that on Earth, phosphine is almost exclusively produced by anaerobic bacteria, thriving in oxygen-free environments like swamps and animal guts. Finding it floating in the clouds of an alien planet isn't just unexpected. It's the kind of anomaly that makes astronomers drop their coffee and double-check their data. The planet in question orbits a dim red dwarf star, its atmosphere a swirling mix of hydrogen and carbon dioxide, conditions where phosphine shouldn't last more than a few hours before breaking down. Yet there it is, stubbornly reappearing in spectral analyzers like a cosmic ghost. The immediate question isn't just how it got there, but why. On Earth, life is phosphine's most efficient factory, which is why scientists first dared to whisper the L word, biology. Could microbial organisms be floating in this world's upper atmosphere, churning out phosphine as a byproduct of their metabolism, just like their earthly counterparts? But before we rewrite the biology textbooks, there's a catch. Phosphine can also form through extreme abiotic processes, volcanic activity, lightning in phosphorus-rich environments, or even chemical reactions deep within gas giants. The challenge is that this planet doesn't neatly fit any of those scenarios. It's not hot enough for volcanic phosphine production, nor does it have the crushing pressures of a gas giant. That leaves two possibilities. Either we're missing some exotic new chemistry that can forge phosphine under unexpected conditions, or we're staring at the first credible hint of alien life. The hunt for answers has turned into a high-stakes detective story. Teams are scouring the planet's atmospheric data for other biosignatures, molecules like methane or oxygen that might hint at a biological cycle. Others are modeling every conceivable non-living process that could explain the phosphine, from meteorite impacts to unknown photochemical reactions. Meanwhile, next-generation telescopes are being trained on this world, their instruments fine-tuned to catch the faintest whispers of chemistry that might tip the scales toward life or toward an even stranger geologic mystery. What makes this discovery so electrifying isn't just the potential for life. It's the reminder that the universe loves to defy our expectations. Even if this phosphine turns out to have a non-biological origin, it's forcing us to expand our understanding of planetary chemistry. And if it doesn't, then we might be standing at the threshold of the greatest discovery in human history, a clue that we're not alone, hidden in the toxic clouds of a world light years away. Either way, this exoplanet has already done something remarkable. It's made us question with renewed urgency what it truly means for a planet to be alive. Picture a planet fleeing its own destruction, not with a fiery explosion, but with a quiet, almost mournful trail of dust stretching millions of kilometers behind it like a cosmic comet. This isn't the aftermath of a collision. It's an exoplanet caught in the act of shedding its own skin, its surface so volatile that eruptions or impacts constantly blast material into space, forming a ghostly tail that glints in the starlight. Scientists first spotted this world not by its silhouette against its star, but by the way its dusty veil scattered light, creating a flickering spectral signature unlike anything seen before. What's startling isn't just the tail itself, it's what the tail implies about the planet's hidden turmoil. On Earth, volcanic activity is sporadic, with decades passing between major eruptions. But here, the sheer volume of dust suggests a world in perpetual upheaval, where lava fountains or asteroid bombardments occur on a scale that would dwarf Earth's most violent epochs. Some researchers theorize this could be a super-Earth with a hyperactive core, its mantle churning so aggressively that it routinely cracks the crust open like an overripe fruit. Others wonder if the planet is trapped in a cosmic shooting gallery, orbiting through a debris field thick enough to pummel its surface with non-stop impacts, kicking up dust like a truck barreling down a dirt road. The real intrigue lies in what this tale reveals about planetary evolution. Normally, atmospheres thin out over time as gases escape into space, but this world seems to be doing the opposite, leaking solid matter instead, like a sieve straining pebbles. That could mean its geology is so extreme it's essentially unraveling, shedding mass faster than gravity can hold it together. Alternatively, the dust might be temporary, a symptom of youthful growing pains. After all, early Earth endured similar chaos during the late heavy bombardment, when asteroids rained down so frequently they turned the sky molten. If that's the case, we might be witnessing a planetary phase no one's ever caught before. A world mid-transformation, its tale a fleeting snapshot of cosmic adolescence. But here's the most tantalizing possibility. That dust could be more than debris, it might be a messenger. Just as geologists read Earth's history in layers of sedimentary rock, astronomers could analyze the composition of this tale to decode the planet's interior. Minerals vaporized by eruptions or impacts might carry chemical fingerprints of underground oceans, metallic cores, or even, if we're lucky, unusual concentrations of elements like phosphorus or sulfur, which on Earth often accompany biologic activity. The universe loves its dramatic exits, but this planet's dusty farewell isn't just a spectacle, it's a clue. Every grain spiraling into the void tells a story about how worlds are born, how they suffer, and how sometimes they leave a little of themselves behind in the darkness. And if we're listening closely, those stories might just rewrite what we know about the life cycles of planets, one glowing particle at a time. Some planets don't just have weather, they have entire atmospheres moving to a different rhythm than the ground below. Imagine standing on the surface of an exoplanet where the air above you races around the planet at thousands of kilometers per hour, while the ground beneath your feet crawls at a snail's pace. This bizarre disconnect isn't science fiction, it's a phenomenon called superrotation, and on this distant world, it's turned up to 11. Venus, our solar system's poster child for superrotation, has upper winds that circle the planet every 4 Earth days faster than the planet's own sluggish rotation of 243 days. But this exoplanet takes that imbalance to staggering new heights. Here, the atmosphere doesn't just lap the surface, it blurs into a supersonic frenzy, with jet streams roaring at speeds that could cross continents in minutes. The cause, a mix of stellar heating and the planet's own peculiar rotation. Unlike Earth, where sunlight spreads relatively evenly, this world's tidal locking ensures one side bakes endlessly under its star's glare while the other languishes in eternal night. That extreme temperature difference acts like a colossal engine, driving winds that spiral upward and accelerate until they become an atmospheric freight train. But here's the real mystery. How does this super-rotating layer interact with the sluggish surface below? On Venus, the thick carbon dioxide atmosphere buffers the disconnect, but this exoplanet's composition is different, possibly thinner, with layers that shear against each other like sheets of ice slipping over a frozen lake. Some researchers suggest the boundary between these two realms could generate constant electrical storms, as differing wind speeds create friction powerful enough to ionize the air. Others speculate the jet stream might act like a blender, churning chemicals between atmospheric layers in ways that could, under the right conditions, spark unexpected chemistry. The implications stretch far beyond this single world. By studying superrotation at such extremes, scientists are cracking open fundamental questions about how energy moves through planetary atmospheres. Why do some worlds let their upper skies break free, while others like Earth keep their air and surface tightly synchronized? The answer could reshape how we model climates on exoplanets, including those in the habitable zone. After all, if a planet's upper atmosphere is darting around like a hummingbird while its surface trudges along, that could redistribute heat in ways our current simulations don't account for, may be turning what looks like a frozen wasteland into a world with temperate pockets, or vice versa. What's truly humbling is how discoveries like this expose the limits of our Earth-centric assumptions. We're used to a world where the sky and ground move in relative harmony, where weather is tethered to geography. But the universe keeps reminding us there are stranger rhythms out there, entire planets dancing to atmospheric beats we're only beginning to hear. And with each new exoplanet that defies the textbook, we're not just learning about distant worlds, we're learning how little we've truly grasped the full symphony of planetary possibilities. Beneath a fractured, cratered surface that looks frozen in time, this exoplanet hides a secret. Its mantle doesn't just simmer in darkness, it glows. Infrared telescopes have spotted eerie ribbons of light seeping through cracks in the crust, betraying the presence of a vast, partially molten layer beneath. Unlike Earth's mostly solid mantle, this world's interior churns with pockets of liquid rock so hot they emit their own radiation, painting the planet's scars with a faint, otherworldly luminescence. It's as if the planet itself is bleeding light from wounds that never heal. What makes this discovery so startling isn't just the spectacle, it's the energy it represents. All that heat isn't trapped, it's escaping, fueling geothermal activity that could rewrite the rules of habitability. On Earth, similar heat drives volcanic vents on ocean floors, creating oases where life thrives without sunlight. Here, even if the surface is barren, underground reservoirs could bubble with warmth, melting ice into hidden aquifers or powering chemical reactions in pitch-black caves. Suddenly, a planet that seemed geologically dead becomes a contender in the search for life, not despite its fractures, but because of them. The implications ripple far beyond this single world. We've long assumed that planets too small or too distant to retain atmospheric heat were biological dead ends. But if molten mantles can persist radiating energy through cracks like a cosmic radiator, then even rogue planets drifting between stars might carry subterranean furnaces capable of sustaining chemistry for eons. Imagine microbial ecosystems clustered around deep sea vents, not in oceans of water, but in slurries of liquid ammonia or hydrocarbons, thriving in temperatures that would boil Earth's toughest extremophiles. Yet the most profound twist lies in the glow itself. Normally, we search for life by looking for reflected starlight or atmospheric gases, but this planet suggests another way, hunting for the infrared signatures of geothermal activity, the thermal fingerprints of worlds keeping themselves warm from the inside out. Future telescopes tuned to these wavelengths might reveal a hidden population of planets glowing faintly in the dark, their heat not a relic of formation, but an ongoing spark, proof that even in the coldest corners of space, fire still flickers beneath the stone. And where there's warmth, there's always a chance, however slim, that something might stir in the depths. Most moons follow a simple rhythm, one planet, one orbit, like dancers twirling around a single partner. But this exoplanet plays host to something far more intricate. A pair of moons locked in their own gravitational embrace, circling each other as they spiral around their parent world in a celestial waltz. It's as if Earth's moon had a twin, and the two orbited one another while still tracing their path around our planet, a rare and delicate arrangement that turns this distant system into a gravitational funhouse. What makes this binary moon system so extraordinary isn't just the poetry of their dance. It's the chaos it unleashes beneath their surfaces. Every pass, every tug between these moons generates tidal forces so intense they flex the very rock of their interiors, creating friction that could melt ice into hidden oceans. We've seen hints of this on Jupiter's moon Europa, where tidal heating from the gas giant's gravity keeps a subsurface sea liquid. But here, the heat comes from two directions, the planet's pull and the moon's own relentless orbits around each other. The result, a double-barreled geothermal engine that could turn these moons into cosmic pressure cookers simmering with energy. The implications for life are tantalizing. If one tidal heat source can sustain the oceans of Enceladus or Europa, could two create even more stable or more extreme environments? Picture a world where hydrothermal vents don't just dot the ocean floor but thread through it like a labyrinth, fueled by constant seismic shudders from above. Or imagine tides so violent they churn nutrients through the water column like a whirlpool, creating currents that might ferry life's building blocks between depths and shallows. But there's a catch to this frenetic energy. Too much tidal heating could boil away a moon's oceans or fracture its crust into volcanic chaos. The key lies in the delicate balance between warmth and destruction, a balance these moons might have struck perfectly or catastrophically. Scientists are racing to model their orbits, searching for clues about whether their interiors are temperate seas or molten ruin. The real magic of this discovery. It's a reminder that habitable real estate might not be limited to planets at all. Moons, especially those with partners, could outnumber planets in the galaxy by the billions. And if even a fraction of them have the right gravitational recipe for subsurface oceans, then the universe's potential for life just expanded far beyond the neat circle of a star's habitable zone. Suddenly, the most promising places to look for aliens might not be Earth-like worlds at all, but moonlit oceans shimmering under the push and pull of a double dance. Imagine stepping onto a world where winter doesn't just bring snowflakes, it brings blizzards of dry ice cascading from the sky in glittering crystals of frozen carbon dioxide. This isn't a scene from a futuristic novel. It's the reality of an exoplanet where the atmosphere itself freezes solid, draping the landscape in eerie, frost-like sheets of CO2. Unlike Earth's water-based snow, this planet's version of a winter wonderland is built from the same gas we exhale with every breath. Only here, it's cold enough to turn it into a seasonal blanket of alien ice. What makes this discovery so revolutionary isn't just the novelty of carbon dioxide snow. It's how it mirrors Earth's climate cycles in uncanny ways. Just as our planet's water cycles between ice caps and vapor, this world's CO2 shuttles between atmosphere and surface with the changing seasons. When temperatures plummet, carbon dioxide freezes out of the air, piling into polar caps of dry ice that glint under the dim light of a distant sun. Then, as the planet tilts toward warmer months, these caps sublimate back into gas, thickening the atmosphere and altering global pressure patterns. It's a climatic tango eerily reminiscent of Earth's own seasonal shifts, but with a chemistry straight out of a lab experiment gone wild. The implications for planetary science are staggering. We've long assumed that water was the universal solvent driving weather systems, but here's a world where carbon dioxide takes center stage, proving that nature has more than one script for climate drama. The way CO2 cycles between solid and gas could even influence wind patterns, creating jet streams and storms fueled not by water vapor, but by the rise and fall of dry ice. Picture hurricanes with cores of condensed carbon dioxide, or blizzards that don't melt but vanish straight into thin air. Yet the most tantalizing question isn't about weather, it's about time. Earth's climate history is written in layers of ice cores, trapping ancient air bubbles like tiny time capsules. If this exoplanet's dry ice caps preserve similar records, they could offer a frozen archive of atmospheric changes stretching back millennia. Future missions armed with spectrometers tuned to carbon dioxide secrets might one day decode these layers, revealing how the planet's climate has evolved, or whether it's teetering on the edge of a CO2-driven tipping point. What's truly humbling is how discoveries like this stretch the boundaries of Earth-like. We search for familiar features, oceans, oxygen, temperate zones, but the universe keeps handing us worlds that follow the same rhythms with entirely different ingredients. A planet where the snow isn't water, the air isn't nitrogen, and yet the dance of seasons feels hauntingly recognizable. It's a reminder that nature doesn't need our blueprint to create complexity. Just a few basic laws, a sprinkle of chaos, and the patience to let time work its magic. And somewhere out there, another world might be turning its own version of winter into art, painting its peaks with frost we've yet to imagine. Deep within this colossal exoplanet, where pressures reach values so extreme they distort the very fabric of matter, lies an enigma wrapped in an invisible shroud, a planetary core drowned in an ocean of liquid helium. Unlike Jupiter, where hydrogen dominates the interior, this world's heart is smothered under a swirling, superfluid blanket of helium so dense it behaves more like a liquid metal than a gas. The crushing weight of the atmosphere above forces the helium into states that defy everyday intuition, a substance simultaneously fluid and conductive, capable of conducting heat with almost no resistance while enveloping the core in near-perfect insulation. This discovery isn't just about adding another oddity to the exoplanet catalog. It's like stumbling upon a cosmic Rosetta Stone for deciphering how gas giants are built. For decades, planetary scientists relied on models suggesting giant planets have layered interiors, rocky cores wrapped in metallic hydrogen, topped by gaseous atmospheres. But here, the helium layer throws a wrench into that tidy framework. Instead of sitting idly between layers, it acts like a thermal dam, trapping the core's heat and potentially altering how energy ripples through the planet's depths. Some researchers speculate this could explain why certain gas giants emit more heat than expected. Their helium blankets might be hiding reservoirs of primordial warmth, leftovers from their violent births billions of years ago. The implications ripple outward. If helium can form such insulating layers, what other exotic barriers might exist inside planets we've yet to discover? Could there be worlds where helium mixes with heavier elements, creating hybrid fluids with bizarre magnetic properties, or cores so isolated by these layers that they remain molten far longer than physics predicts? Every new data point from this exoplanet forces astronomers to revisit their simulations, tweaking equations to account for behaviors no lab on Earth can replicate. Yet the real intrigue lies in what this means for planetary evolution. In our solar system, Jupiter and Saturn are helium-rich, but nothing like this. If such extreme helium layers are common elsewhere, it could mean gas giants aren't just oversized versions of each other. They might diverge into distinct subclasses based on hidden interior chemistry. A planet like this could represent the missing link between traditional gas giants and something entirely new, a helium world variant, its history locked inside that shimmering alien ocean. And that's the thrill of discoveries like this. They don't just answer questions, they reveal how much we've underestimated the universe's creativity. Every layer peeled back exposes another mystery, another twist in the story of how planets grow, age, and defy our expectations. Who knows what other secrets might be lurking beneath the clouds of distant worlds, waiting for the right telescope or the right curious mind to bring them into the light. Some planets don't orbit their stars, they escape them, following paths so stretched they seem to flirt with freedom at every turn. Meet the exoplanet on the ultimate cosmic joyride, a world tracing a hyperbolic orbit so extreme it barely clings to its star's gravity, swinging in for a fleeting encounter before slingshotting back toward the void. Unlike the neat ellipses of most planetary orbits, this path looks like a celestial smile stretched to breaking point, a trajectory so rare it shouldn't exist without cosmic intervention. What makes this discovery so revolutionary isn't just the orbit's shape, it's the story written in its chaos. Normally, planets form alongside their stars from the same spinning disk of gas and dust, settling into stable, near-circular orbits over time. But this world moves like an interstellar hitchhiker, its wild path suggesting it was either stolen from another star system or violently kicked into this extreme trajectory by a close encounter with a hidden black hole or rogue planet. It's the astronomical equivalent of finding a bullet lodged in a tree and realizing the gun was fired from another county. The implications ripple far beyond a single rogue world. If hyperbolic orbits are more common than we thought, entire planetary systems might be far less stable than our own. Imagine a cosmic game of pinball where gravitational encounters between stars or dark objects routinely fling planets into bizarre paths. Some might become interstellar nomads, forever adrift between stars. Others, like this one, could be temporarily captured by a new star's gravity, doomed to an unstable relationship that'll eventually eject them back into darkness. Yet here's the tantalizing twist: this planet's extreme orbit might actually be its salvation. While most worlds bake or freeze based on their distance from a star, this one experiences seasons on overdrive, brief, scorching close approaches followed by long, frigid retreats. Some astrobiologists speculate that such rhythmic extremes could actually encourage adaptation, with life forms evolving to hibernate through deep freezes and bloom during fleeting warm periods. It's a long shot, but nature has a way of finding opportunities in the unlikeliest places. What's truly humbling is how this discovery exposes the fragility of our solar system's quiet order. We take our stable orbits for granted, but the universe reminds us they're just one possible outcome in a ballet where gravity writes the rules. And sometimes, those rules include a planet that dances on the edge of escape, a celestial rebel rewriting what we thought possible with every reckless loop around its star. The sky above this alien world doesn't just shimmer. It breathes with light, pulsing in rhythmic waves like the glow of fireflies on a summer night. Unlike Earth's auroras fueled by solar winds or the reflected hues of a sunset, this exoplanet's atmosphere generates its own otherworldly luminescence. Chemical reactions between high-energy compounds in its upper layers produce a faint, ethereal radiance, casting the clouds in an eerie, self-made halo. It's as if the planet itself is whispering to the cosmos in flashes of bioluminescent code. What makes this phenomenon so mesmerizing isn't just the spectacle, it's the uncanny resemblance to biological light shows on Earth. In our oceans, creatures like jellyfish and plankton use luciferin molecules to create glowing displays for communication or camouflage. Here, the light arises from a purely abiotic dance of nitrogen, oxygen, and trace metals ionized by stellar radiation, nature's chemistry set running on autopilot. Yet the parallels are undeniable, forcing scientists to confront a tantalizing question. If non-living chemistry can mimic bioluminescence so precisely, could life on this planet or elsewhere have evolved to harness these reactions for its own purposes? The debate hinges on efficiency. On Earth, bioluminescence requires energy, but it's a net gain for organisms that use it to attract mates or lure prey. On this exoplanet, the atmospheric glow is a byproduct of chaotic reactions, a wasteful process unless something were actively channeling it. Some theorists propose that microbial life floating in the upper clouds could exploit the faint light for photosynthesis like energy capture, turning a random spark into a survival tool. Others argue the radiation needed to sustain the reactions would shred organic molecules faster than any hypothetical life could adapt. But the real significance of this discovery lies in the toolkit it gives astrobiologists. Until now, biosignature searches focused on gases like oxygen or methane. This planet teaches us to look for subtler clues, patterns in light, rhythmic pulses that defy simple chemistry, or spectral fingerprints hinting at molecular cooperation. Future telescopes might scan exoplanet atmospheres not just for ingredients of life, but for its potential handiwork, lights left on in the cosmic dark, intentional or otherwise. Perhaps the most humbling lesson is how blurry the line between chemistry and biology can be. A glow that begins as random reactions might, under the right pressures, become the first language of life. Or it might remain a beautiful accident, a reminder that the universe doesn't need life to create wonder, just a handful of elements and a spark. Either way, this world's luminous skies challenge us to rethink where and how we search for living light in the void. From diamond rains to glowing atmospheres, these 30 discoveries prove the cosmos thrives on rewriting the rules. Every time we think we've seen it all, a planet where titanium clouds act like celestial sunscreen, or another where hurricanes rage for centuries, the universe fires back with something even wilder. These aren't just curiosities, they're cosmic breadcrumbs, each one hinting at processes and possibilities that challenge our very definition of a planet. Take volcanic super-Earths with lava oceans, or rogue worlds glowing with self-made auroras. None of them fit the tidy categories we once used to box planetary science into. And that's the point. Every bizarre exoplanet we uncover isn't just expanding the catalogue of weird worlds. It's forcing us to tear up the textbook and start fresh. What good is a habitable zone when life might lurk in subsurface oceans on frozen outcasts? How do we define atmosphere when some planets wear layers like a cake, each with its own chemistry and weather? The most exciting part, we're only scratching the surface. Right now, next-generation telescopes like the James Webb Space Telescope are peeling back the layers of these alien skies, while missions on the drawing board promise to map exoplanet surfaces in unprecedented detail. Who knows what we'll find next? A world where silicon-based life thrives in molten rock valleys, or a moon where ammonia waterfalls carve canyons into ice. The tools we're building today could reveal answers to questions we haven't even thought to ask yet. But here's the real magic: you're part of this story too. Every time you gaze up at the night sky and wonder what's out there, you're tapping into the same curiosity driving these discoveries. So tell us, which of these 30 exoplanets left you awestruck? Was it the diamond-shrouded super-Earth or the planet with triple sunrises? Drop your thoughts in the comments. Hit like if you're as hooked on these cosmic mysteries as we are, and subscribe to join us on the next leg of this journey. Because the universe isn't just stranger than we imagine, it's stranger than we can imagine, and together we're just getting started.